Hello ST314. This video is to show you how to do a multiple linear regression analysis in Minitab. The example data that we'll be using is the ST314 MLR Dimensionless factor. If you click on here or double click and press open, it will automatically open a Minitab worksheet. Okay, so now we have our data. And what is the question of interest here? So some researchers wanted to know the relationship among superficial fluid velocity, the liquid viscosity, and the mesh size of the openings on a dimensionless factor that was used to describe the pressure drops in a screen plate bubble column. Okay, so we have a quantitative response variable here, y. Okay, this is the dimensionless factor. And then we have three explanatory variables: velocity, viscosity, and size. Okay, which all also look to be quantitative. All right, so this is multiple linear regression because we have more than one explanatory variable. Okay, so in multiple linear regression, there isn't necessarily a quick visual tool to use like simple linear regression. We could do a scatter plot of the response variable versus each one of the explanatory variables individually to see if individually they each have a relationship. However, this can get very tedious if you have multiple explanatory variables. So here we're going to just proceed directly to the regression analysis. So we go to stat, regression, and here our response variable is y, the dimensionless factor, and our explanatory variables are size, viscosity, and velocity. All right, again, like we did with the simple linear regression case, we want to choose the results to be a little minimized. So again, Minitab just gives us too much information, so we press OK. And let's also get our residuals for this. So we always want to just kind of look at our residuals. It's actually kind of an ongoing process. Doing a regression analysis, look at the residuals. How do they look? Okay, they look okay, then move forward. All right, so we continue to kind of do that process whenever we're doing any sort of regression analysis. All right, go ahead and press OK. I'm going to move the residuals aside so I can look at my analysis of variance table. Now, the analysis of variance table is very useful in multiple linear regression. Now, in simple linear regression, the p-value from the F statistic is the same corresponding p-value that you would get for the slope test from the slope t-test p-value. So the p-values will be the exact same thing. It's basically the same test. Okay, but here with multiple linear regression, we are testing whether or not all of the beta coefficients are equal to 0 is our null hypothesis, and our alternative hypothesis is that at least one of those is not equal to 0. So if at least one of those is not equal to 0, then that means that we have a model with at least one significant predictor. If we have a model that has at least one significant predictor, then we can move on to the next step and look at each individual explanatory variable to see whether or not it is a significant predictor for our response. Here we can see that our p-value is quite a bit less than 0.01. Because we have 3 zeros there, that doesn't mean that we have a p-value of 0. We just have a p-value that's less than 0.001. Okay. So this analysis of variance table is very helpful. It can tell us several things. We can actually calculate the R-squared coefficient from this as well. Now Minitab gives it to us up here, 81.2, but we could also use this ANOVA table to calculate this R-squared value. If we know the values in the ANOVA table, then we can simply just divide the sum of squares the sum of squares regression divided by the sum of squares total is our R-squared value. So SS reg divided by SS total is our R-squared value. It's the proportion of variation that's explained by our model. Now let's go back to this F statistic. We're testing whether or not the beta all the beta coefficients are equal to 0, and the alternative is at least one of them is significant. We can see that our p-value is very small, so it looks like one of our explanatory variables is a significant predictor of the dimensionless factor y. So what do we do from here then? After we look at the F statistic, then we can move on to the individual T statistics. So just move on up. The regression output actually gives us this as well. Now this looks very similar to the regression output analysis when a simple linear regression, except now we have the other variables. However, it can be read the same way. We can see that the size p-value for the test statistic on the estimate of size is equal to 0.131. This is a relatively large p-value, and so this might provide no evidence that the size coefficient is really anything other than 0. Next up, we have the velocity estimate. It is too much larger than 0.05. So we might drop these from the model. So let's redo an analysis and remove one by one the velocity variable and see how that changes our model. So we go up to stat, regression, regression, and we can simply just delete velocity from the model. Press OK. Now it looks like our residuals still look pretty nice. Okay, maybe there's something happening here, but let's ignore that for a moment. Okay, and we still see that now the viscosity still looks like to be a pretty significant predictor, but size is still over 0.05. Okay, notice though how the p-value changed of the size when I removed the velocity term. Okay, so now what that means is that because the viscosity is gone, or excuse me, because the velocity is gone, the size coefficient might be explaining a little bit more of our response variable than it was before when velocity was in the model. That's why we need to drop the explanatory variables one by one to see how they then change our model. Okay, but still size does not look like it's a significant predictor of the dimensionless response variable y, so let's drop that too from the model. So stat, regression, regression, remove size, press OK, and here we are. We have now a simple linear regression. We have a significant predictor, viscosity, and we have a regression equation up here to predict the dimensionless factor y. Okay, so how can we kind of describe this? Well, let's describe this process a little bit more formally. Superficial fluid velocity and the mesh size of the openings were just not significant predictors of the dimensionless factor used to describe the pressure drops in the screen plate bubble column. Basically, they had p-values that were over our significance level that we were willing to take, so 0.05. Therefore, they were dropped from the model. So now that we're looking at the final model, there's convincing evidence that the liquid viscosity is a strong predictor. The model estimates for every 1 unit change in viscosity, the dimensionless factor used to describe the pressure drops in a screen plate bubble column changes by 0.247. And we can see that here in our equation. Okay, now furthermore, we could actually then do a confidence interval for our coefficient on viscosity if we'd like to. Here, I don't have us doing that in this problem, but it is something that you could do, just like we did in the simple linear regression case. Notice too how the R squared has changed from before. 77.6 now, instead of the 81.2% it was when the other factors were in the model. Note that the R squared value will always increase the more variables you add to the model. And so sometimes it's not good to trust this value wholeheartedly. It doesn't even matter if you add values that are not significant predictors. It simply will increase because you're adding more models or adding more explanatory variables to the model. So just beware of that. Okay, now finally we need to look at the residuals. Okay, so for this particular problem we do have some more observations. So we have some more residuals to look at. It looks like the normality assumption is met here. We have a pretty much normal curve, symmetric. Here we can look at that again in the probability plot. We can see most of the observations are lying along this particular line. Now here with the fitted versus residuals plot, we can see that possibly there's two distinct outliers here in the x direction. However, they're not necessarily varying widely in the residuals. So we're not going to be too concerned about these. Perhaps these are maybe of some sort of population though that we might need to look back and be concerned with when we look at our data. Okay, lastly, are the observations independent? It looks like yes, they are. There's not necessarily a distinct pattern in the observation order of the residuals. Okay. So the main point of multiple linear regression is really looking at the analysis of variance table and being able to understand what the F statistic is telling us. What are the sums of squares? What are the mean squares? How do we calculate the F statistic? If you notice, if we are just given the degrees of freedom and the sum of squares, we can actually then recreate the rest of the table. The mean sum of squares are just simply the sum of squares divided by the degrees of freedom. This is the mean square for the regression. This is the mean square for the residuals. To find this, we just simply take the sum of squares for the residuals and divide it by 17, the degrees of freedom for the residuals. All right, and to get the F statistic, we simply then take the quotient of the two mean squared errors. So 1206.7 divided by 20.5 would give us an F statistic of 59. Finally, we can look into table 4 to find our p-values. Okay, one last little note is that an F distribution has 2 degrees of freedom, a numerator degrees of freedom and a denominator degrees of freedom. How to find those are pretty simple. The degrees of freedom for the regression is our numerator degrees of freedom. The denominator degrees of freedom are the residual error degrees of freedom. So these are denoted as K, the number of parameters that are in my model, okay, and the residual error, or excuse me, K is the number of explanatory variables that are in your model, and the residual error degrees of freedom is N minus K minus 1, which is 17 in this case. Okay, so you should have all the tools to be able to perform a multiple linear regression analysis, read an analysis of variance table, and read regression output. These are things that I find are really important and will be tested on the final exam.